The other thing we want to understand is when does my intervention have no effect on this other variable that I'm interested in, right? So you intervene, nothing is changing. If you can read this off from the graph, that will be very valuable, right? So here we say that if the only connections between the two variables are through backdoor paths, the paths that start with an incoming edge, then I can say intervention will have no effect on the target variable. So here, if I intervene on z here, right, it's going to affect y, but it's not going to affect u. U is still going to be sampled from its marginal distribution, and x is going to be sampled from its conditional p of x given u, and that's it. So we can say that p of x given z, do z in this graph is the same as p of x. Distribution of x is not affected by my intervention. Okay? And you can assess this by removing the incoming edges from z here, and checking whether x and z are deseparated in that graph. Okay? This is again a simplified version of the calculus rule 3. And as you can see, our goal is to go from interventional quantities to observational quantities because this is something we can measure. Okay, a third example that's a little more complicated. Let's say here I'm interested in evaluating p of y given do z. Right? So now let's test the cases we covered. If I intervene on z, does it have any causal effect on y? Because if not, this will be just p of y. And here, yes, there's a directed path going from z to y, so p of y given do z is not the same as p of y. Okay, but maybe I can replace the intervention with conditioning. So can I say p of y given do z is the same as p of y given z? Let's see, if I condition on z, that affects x, that affects u, that affects y. So no, that's not true. Conditioning has a different effect than intervention here. So they're not the same. Does it mean I give up? Right, that's it? No, I can still do something. So if I can somehow block the path that goes through here from z to y, right, then actually I can replace intervention with conditioning. Okay, so how will I do that? So it's always a good idea to write this query as a marginalization of a joint interventional distribution. So you write this as p of yx given to z, and you unpack it because it's a valid probability distribution. I can use chain rule of probability, and I can write this as a summation over x. Right? Now, what do I know here about these two terms? Let's start from here. I know that if I intervene on z, this has no causal effect on x, so this is the same as p of x. So I can replace this p of x given to z with p of x. Right? How about this term? P of y given x comma do z. If I intervene on z, right, and if I condition on x, or in other words, if I already conditioned on x, then intervening on z or conditioning on z are the same, because there is no active vector path from z to y. X is already blocking that path. X has already done the posterior update. So further conditioning on z is not going to change anything about the upstream variables. Okay? So that's why I can actually replace this do z with a conditioning variable. So this is actually p of y given x and z. Okay? So I applied the calculus rules, the two rules together here. If I put it together, I'm going to get this formula. P of y given do z is the same as p of y given xc times p of x summed over x. And now notice this does not simplify because this is not any kind of probability, and this is known as the backdoor adjustment formula. Okay, and this is how you derive it from first principles. Any question about this? So if you are interested in the general versions of these rules, this is a screenshot from the original paper of Bird from 95, and he has these three rules, and later on they were proven to be complete for converting any interventional distribution to a function of potentially a very complicated function of the observational distribution. Now, I'll just show some examples to give you a feel of what these might look like. And it is going to be scary, but don't worry. We have the algorithms to do this, so you don't have to do this by hand. So let's say you have these graphs, right? 4 different graphs. And here, just for some, to give you the notation, if you see a bidirected edge that is dashed, that means there is a latent variable that is affecting the 2 variables that it is attached to, right? So here there is a latent confounder affecting R and Y at the same time. And that's okay. So if you want to understand P of Y given to X in any of these graphs, how do the expressions look like? There is no X on that graph, so that would be P of X given to R. So this first one is called the napkin graph. It's called by Per, and I think it's the first example where vector and or front door adjustment is not sufficient, so you have to do something else. And you get this ratio expression that you need to evaluate to get to this causal effect in the napkin graph. Because this can be seen as a conditional distribution in some interventional distribution. That's why. Okay, so that looks complicated already, right? How about the second graph? Well, there you get this. Okay, there's no ratio, it's just sum of bunch of terms, but you have a lot of terms, right? You have a lot of terms you need to compute. How about the third graph? You get this. Now you have a ratio and multiplication with some other terms, that all of which you need to estimate from data, right? And the final graph looks like this. Okay, and these things usually don't simplify further. So what does this tell me? Let's say you don't know the graph. Let's say you don't know these expressions. Okay, how can you hope to estimate causal effect? Because this is literally what you need to evaluate, right? So the takeaway here that I want to give is that you cannot hope to estimate these quantities if you don't have the identification formula, right? If you don't have the expression of these interventional distributions in terms of the observational distribution. And just a little note here, all of these are taken from causalfusion.net website that was developed by Elias Birnbaum. So if you don't know about it, check it out. It's very, very useful to get to these expressions. Okay, good. So I have just this one slide to put the two frameworks into context, okay, to the best of my abilities. So on the left, you see Per structural causal models, and on the right, you see Rubin-Neyman potential outcomes framework. And how are they different? Now, they have been proven to solve the exact same set of problems, proven to be identical, right, in some sense, but they differ in the way you phrase things typically, right? So how do they differ? In SCMs, you start with an assumption. You start by assuming that there's a set of structural equations that are unknown to you, but that's how the system works. There are those set of structural equations, and we interpret them as assignment operators. So you go from the input to the function to the output of the function, never the other way around, right? It's directional. And then, after you assume a set of structural equations, you define the intervention on these equations. Okay? Whereas if you go to potential outcomes, you start by first defining the counterfactual variables. So you define y of 1, y of 0, and they live in a joint probability space. You already defined counterfactual probability. Okay? So you start with defining that. And then you make an assumption about how they might be independent from each other, maybe given some set of features. Okay? So it's reversed in PO framework. In SCMs, you try to understand the formula that transforms the observational distribution to interventional distribution, or the other way around, right? How they are related to each other. And in potential outcomes, the focus is mostly on developing estimators that give the causal effect directly under the independence assumptions mentioned above. Okay, so this is my take on some of the high-level differences between these two frameworks, if you want to understand that. Okay, I'm going to talk about neural networks very briefly, but before that, are there any questions? Okay, so let's talk about neural networks. Again, I'm assuming everybody knows neural networks. This is going to be very brief. So what are neural networks good for? They are good for solving this age-old problem, very important problem, muffin versus Chua right? So if you want to detect which one is a dog species and which one is a muffin, then we finally solve this problem using neural networks, right? So it's a classification problem, and it looks funny and it looks easy enough, right? But it's actually a very complicated problem because the function you are trying to learn here is a very, very complicated function that goes from this image, which is a high-dimensional matrix or a tensor, to a scalar, right? 0 or none. So this is a classification problem. And now today we have all these architectures that can solve a variety of these problems very, very easily. For example, multi-layer perceptron, a simple architecture looks like this, and it basically solves the MNIST, right? Just a couple of lines today. And we also know some of the more modern success stories of neural networks, right? So for example, we have AlphaGo, that uses deep reinforcement learning, search, self-play, and so on, that solved the Go problem, at least better than humans could, finally. We have AlphaZero, which does only self-play, and it does not have access to any opening books, and yes, but still it sort of killed chess, right, in terms of ELO. We have AlphaFold that uses attention, and this has solved, or at least made a big progress in one of the most important problems for human beings, as far as I understand. We have Dolly, transformers, and diffusions to generate all these fancy images today, right? We have ChatGPT since 2022. It uses transformers, supervised learning, RLHF, and so on. And recently we had Sora and even more models that I didn't have time to put here. Right? So deep learning has been a revolution, and we are just kind of not going to live without it anymore. Right? And what are some basics of neural networks? You have this kind of feed-forward functions that are efficiently computable, and they are also easy to train because you can do backpropagation and you can parallelize all these computations in a GPU, so you can very efficiently search for a very complicated function, minimizing a differentiable loss function.